Good morning once again. So, as a part of summarizing the previous session, so now I am going to show you a matching pair. So, randomly I'll call one of you, so you can just allow me to or suggest me the correct one. Okay. So, we are going to make everything disappear, whatever which is going to appear on the screen. Okay, on the screen you can see some terms. So last class we have seen some important definitions regarding magnetic materials. So you just observe this for a while, okay, and one of you can start by matching it. Hemant, Hemant, Hemant Reddy, Hemant Reddy,
Initial, ma'am.
K.
Yeah, it's me, ma'am.
Yes, you. Yes. I need one matching pair now. Choose one and match it with, for example, a space around the magnet where magnetic effect is felt.
Okay, ma'am.
So to which one I have to match?
Space around the
Space around the magnet where the magnetic effect is felt. So it was actually a definition of one term. So
magnetic
everybody
field, ma'am.
please, yes, let us check whether it matches with magnetic field. Yes, it diminished away. Okay, like that we are going to do similar kind of
Yeah.
thing. So
It's a
now the
correct,
next.
ma'am.
Yes, what you have said is correct. Thank you,
Thanks.
Hemant. We'll give a next chance to Wahid, SK Wahid.
Yes, ma'am.
Now you just select one pair and we'll check whether it matches.
Unit for magnetic flux density.
Okay, tell me the unit, whether it is in the screen.
Magnetic dipole moment in current carrying wire.
Only choose two things so that it pairs easily. So you have chosen unit for magnetic flux density. To
Yes,
which
ma'am.
one I have to match now? Hope all the terms which is on the screen are familiar to you. Where to match? Where to match this one? Okay, you just think a little bit. Now the chance now goes to Madhusai. Madhusai, B Madhusai.
Ma'am,
Hmm. Now you just match Ra. All simple definitions. You would have written in your note also.
okay, ma'am.
Now don't search for the note. Hmm. Right now everyone should have been realized. All answers are very clear. Who is ready? Okay, anybody can raise hand so that that person can be given a chance. Okay, good. Praveen Kumar Reddy. Good at T. Praveen Kumar Reddy. Come on.
Ma'am, ma'am,
Hmm. Yes, Pa. Now you
unit
raise.
for magnetic flux density is Weber per meter square.
Okay, let me make it Weber per meter square and I'm going to match here. Excellent. Correct. Very good. So for the next question,
Uh,
please give a raise hand button. Next person.
susceptibility.
Any other student, you can just give a raise hand button. So each one can have a chance today. Give a raise hand button. Dinesh, Dinesh, can you match?
Yes, ma'am.
Yes. Which one you are going to select?
Susceptibility.
Susceptibility. Okay. Where to match this one?
Magnetic dipole moment in current carrying wire.
Okay, I'll just take the susceptibility and I'm placing here. But it's rippling away down. It is pushed away. Anybody? Where to match the susceptibility?
B by H.
Yes, who's this?
Abhiram.
Abhiram. Okay, da. I'll just check. Susceptibility B by H. What happened? It is moving away. Shall I check with this I by H?
Yes, ma'am.
Yes, yes, it vanishes. So it accepts. So susceptibility is I by H. And what about this B by H?
Current X area, ma'am.
There, what current into area? This is current into area, not current X area. Current into area. Okay. So this is actually a multiplication symbol which is present in between current and area. Okay. See, very few.
Permeability of free space, ma'am.
Yes, permeability of free space. Where to match this one?
3 into 10 to the power of 7. That's one, ma'am.
Ah, very good. Who's this?
Manikanta, ma'am.
Ah, very good. Right? See, let us match. Expecting for green. Yes, it vanished. Now only two. So what is this? Permeability. Where to
B
match
by
this one?
B by H.
Yes.
B by H.
Permeability is B by H, and the last one will be magnetic
Current.
dipole moment. So this was the second definition we have seen. Dipole, magnetic dipole moment for a current carrying wire can be represented by current into area. So let us match this. So this also vanishes away. Okay, so this is a short, brief summary about what we have learned in the previous session. So in today's session, we will be looking forward for the classification of magnetic materials. So I'm just going to close this one, and now I'm going to share. So concentrate on the class. So you should not take this much of time duration to find out the answer, because everything should be in your fingertips. Because material already given to you, so you should have gone through already. Okay. So this was the previous lesson we have seen. Magnetic parameters, magnetic dipole moment, Bohr magneton, magnetic lines of force, magnetic induction, magnetic field intensity. Magnetic field intensity and magnetic field both are same. Intensity of magnetization, susceptibility, and permeability. These are the important topics we have seen so far. So next is we are moving to the next lesson, dia, para, and ferromagnetism. So classification of magnetic materials. We are going to classify the magnetic materials based on two categories. One is those materials which do not have permanent magnetic moment, and the materials which have permanent magnetic moment. So remember what is meant by a magnetic moment. So both this magnetic moment is associated with purely due to the electron. So the electron's behavior only predicts the behavior of the magnetic material, whether you get the attraction or the repulsion based on the spin magnetic moment of the electron. So if there are spin magnetic moments, then you have three categories: paramagnetic material, ferromagnetic material, and ferrimagnetic material. And for the materials which do not have permanent magnetic moment, we have diamagnetic material. Okay, so among the four magnetic materials, we are going to focus on the first three materials. Actually, in general, in classification of magnetic materials, there are around 11 classification, 11 types of materials are available, but we are going to focus on dia, para, and ferro alone. Okay, in this slide, we have seen types of magnetic materials based on magnetic moment. Okay, this is the first type we are going to see, which is called as diamagnetic material. So in diamagnetic material, you see the word dia. So it is a prefix dia, which means through or across. So in the absence of magnetic field, so you can just look into the atoms. So all are just empty. Okay. So in the absence of magnetic field, all the magnetic moment, there is no magnetic moment inside the diamagnetic material. So diamagnetic materials do not have atomic magnetic moments. So, magnetic moment in an atom is can be considered to be having orbital magnetic moment and spin magnetic moment. So, when you just put together both orbital magnetic moment and spin magnetic moment, we just call by the name atomic magnetic moment. So, if there is no atomic magnetic moment in the absence of external magnetic field, then you say the material to be a diamagnetic material. And when you apply a magnetic field symbol is capital H. When you apply a magnetic field, what happens? The magnetic moments starts to arise. The magnetic moments alignment in the absence of magnetic field we have seen, and in the presence of external magnetic field, the magnetic moments aligns themselves. But when you add all the magnetic moments, the net answer will be zero. So even though when the magnetic field is applied, you can just count the number of magnetic moments 1, 2, 3, 4, 5, 6. So some may point in a reverse direction. So when you add all, the answer will be zero. So this is the case in the diamagnetic material. Even though magnetic moment arises, but when you sum up all, the answer will be zero. So when it is placed under external magnetic field, the atomic magnetic moments are aligned in the opposite direction. So see the direction of the arrows. So each arrows indicates the spin magnetic moment of electron. So each electron is trying to oppose the incoming external magnetic field. So some of the properties we are going to see. So some properties I have drawn already in the screen. So the first property is that, so I've taken a magnetic field. Now the diamagnetic material is placed in the center. Okay, usually what happens, the magnetic lines of force starts from the North Pole and it will end in the South Pole. Starts in the North Pole and it will end in the South Pole. But what does the diamagnetic material do? All the magnetic moments which are developed are pointing in a direction opposite to that of the external applied magnetic field. That's why it just ripples away all the lines of force. Okay, so there is no lines of force that is crossing inside a diamagnetic material because it is has an opposing nature. Okay, and in terms of energy level, you can draw an energy level like this. So when you draw an energy level, in each energy level, we have to place some electrons. Okay, there are some electrons. So there is a criteria for placing these electrons. According to Pauli's exclusion principle, in an energy level, only two electrons can be placed. That too, both electrons should have opposite spin. They should not have the same spin. So this is the Pauli's exclusion principle. Only two electrons of opposite spin can occupy an energy level. Even in chemistry, for writing the electronic configuration of energy state, S, P, D, F, orbitals and all, we would put some box. Within a box, a half spin, one pointing upward direction, the other pointing the downward direction we used to draw. Somebody has unmuted your mic. Just check your mic and just mute for a while. Okay. So I have just drawn some energy levels, increasing order of energy levels, starting from 1 electron volt, 2 electron volt, 3 electron volt, and 4 electron volt. Okay, in order to show the orbital magnetic moment and spin magnetic moment, so do two different colors I have just shown you. The orbital magnetic moment is also pointing in the opposite direction, and spin magnetic moment is also pointing in the opposite direction. Just look upon the energy state of the level 1 electron volt. The energy of the electron is 1 electron volt. Okay, so here the electrons are paired. Okay, the first energy level, the electrons are paired. In the second energy level, the electrons are paired. Third, paired. And fourth, also paired. Since the electrons are paired, there is no unpaired electron which could contribute to the magnetic moment, permanent magnetic moment. Hence, we say in diamagnetic material, there is no permanent magnetic moment. Okay, so this principle of diamagnetic material is applicable in superconductivity. So here in superconductivity, there is a property called as Meissner effect. Meissner effect. So the same rippling nature of lines of force is what we called as a Meissner effect in the case of superconductors. So here a circle shape now, this is a diamagnetic material. When it is placed in the north, between the north and south pole piece of a magnet, automatically what happens? All the lines of force gets repelled away. Okay, clear? So this is the first property. Lines of force are repelled away when diamagnetic material is placed in an external magnetic field. There is no permanent magnetic moment because all the electrons in each levels are paired. There is no unpaired electron present in diamagnetic material. Okay, and the first property we have seen, the lines of force repel, and they repel the magnetic lines of force is the first point. Then we are going to talk about that numerical number, susceptibility, ease with which the material get magnetized. This susceptibility is negative in the case of diamagnetic material, and it is independent of temperature and applied magnetic field. So here the permeability is less than 1, because what is the work of a permeability is to allow or permit the lines of force, but it is less than 1. So see the symbolic representation I made, mu less than 1. So hence there is no permanent dipole moment. So they are called as weak magnets. And the last point is actually repeated from the second point. They are independent of temperature. So when we ask you a descriptive question, discuss about diamagnetic material in detail, you'll just draw the diagram, the energy level diagrams and lines of force diagram, and you will just list out these properties. That's all. So the very first property for all the three types of magnetic materials is you'll talk about the lines of force. Second property, you will talk about the susceptibility. Third one, if it is dependent on temperature or independent of temperature, then permeability value, then whether it has permanent magnetic dipole moment, how it is called, whether it is a strong electron or a weak electron. Okay, on the left side diagram also you can see there is no unpaired electron. So on the top I've just shown you. So while studying this, you can just write and see. Then yellow, susceptibility, negative. Ravanya, I'm just going to remove you. Okay. So hope these properties of diamagnetic materials are clear. So keep in mind, we are going to write about the repelling nature of the lines of force, susceptibility value, then temperature, permeability, dipole moment, the type of magnet, whether it is strong or weak, that's all. So these are the parameters we have to keep in our mind. Then after understanding this, let us see some 7 examples of diamagnetic material. Okay, one by one we are going to see bismuth, phosphorus, antimony, copper, water, alcohol, and hydrogen. So among these, at least if you remember 3 examples is quite enough. Okay, bismuth, phosphorus, antimony, copper, water, alcohol, and hydrogen. These are the 7 examples. So here, this is a pyrolytic carbon. So I'll just show you some of the susceptibility value of diamagnetic material. See, on the left side of the screen, you can see some table with material and the corresponding susceptibility value for starting from superconductor. And the last one is the water. See, in all the examples which I've given you, all takes the value of a negative because diamagnetic material susceptibility is negative. Okay, superconductor, the value is minus 10 power 5, whereas water, it is minus 0.91. So then in the table, you can also see some derivatives of carbon, pyrolytic carbon, diamond carbon, then graphite carbon. Okay, bismuth, neon, mercury, silver, lead, copper are other examples of the diamagnetic material. Now let us see the picture which I have displayed, pyrolytic carbon. So actually there are 4 some golden pieces, some cubes you observe now on the screen. They are nothing but pyrolytic carbon. Actually, these are the black color one, which a hole in the center. This is pyrolytic carbon, and the 4 cubes which are placed on the bottom are nothing but the neodymium magnets. In the second picture, you see some a gap between the pyrolytic carbon and the magnets. This is called as levitation. Okay, there is this air gap because when you place this pyrolytic carbon, because of the opposing nature of the diamagnetic material, you can just place the pyrolytic carbon above the neodymium magnet. There is no interaction between them. Okay, it is one of the largest diamagnetic constant of any room temperature material. Here, a pyrolytic carbon sheet is levitated. Levitated is just elevated upwards because of its repulsion from the strong magnetic field produced by the neodymium magnets. So these are the examples and the corresponding susceptibility value of diamagnetic material. Okay, so the lowest one is water minus 0.91, and the highermost is the superconductor minus 10 power 5. And for the diamond, which is in the middle, it is around minus 2.1. So this alone you can remember. Okay, now we are moving to the next type of material called as paramagnetic material. So like diamagnetic material, here also first of all we'll see the 40 lines of force. How about when you place a paramagnetic material in the magnetic field, what happens? We are going to see now. See here, I place the paramagnetic material in between a north and south pole of a magnet. What does it do? The previous one just repelled away, whereas this paramagnetic material allows the lines of force into it. So it permits the lines of force to pass through it. So here also you can draw the diagram, that is in the absence of magnetic field. So in each atom you can see some arrows inside. Each arrows indicates the magnetic moments of the electron, but they are pointed in different direction. So it just says that even in the absence of magnetic field, magnetic moments are present, but they point in different direction. Okay, when you apply a magnetic field, what happens? All the arrows will orient and they arrange themselves, and they move in a direction parallel to the applied magnetic field. See the direction of the magnetic moments, they are just parallel with the applied magnetic field. All are pointing in the same direction. Okay, so when you go deep into the electronic structure of the paramagnetic material, here also we have some energy levels starting from 1 electron volt, 2 electron volt, 3 electron volt, 4 electron volt. So I've just given an example. This is not the exact value. The lowest energy level is minus 13.6 electron volt. Just for our understanding, I'm just given a example values as 1 electron to 4 electron volt. Okay, now let us fill the electrons level by level. So in the first level, you have 2 electrons. The curved one this is the orbital magnetic moment. The blue one shows the orbital magnetic moment. Both are pointing in the opposite direction. So the black arrow pointing downwards is the spin down, and the black arrow which is pointing towards the top is the spin up. Okay, so both are in opposite direction. They also obey Pauli's exclusion principle, hence they are paired. Moving to the next energy level, you have the same thing. Both are in opposite direction, both spins are opposite, hence they are paired. Likewise, I can check each and every energy level. So on the fourth energy level, I can check that there is presence of only one electron and only one spin. So its pair is missing. So hence there is a presence of unpaired electrons. It is all due to the presence of this unpaired electrons, you get the spin like this. Okay, when both electrons are paired, automatically what happens? This space will be empty. When there is a presence of an unpaired electron, automatically there will be an arrow inside each atom. Okay, this arrow indicates the spin of the electron. Clear? So if unpaired electrons are present, then the material is called as paramagnetic material. When more and more unpaired electrons are present, then the material is called as ferromagnetic material. Okay, so after understanding about the lines of force and the energy levels and unpaired electrons, now we are going to see or list some properties of paramagnetic materials now. Okay, now let us do the properties. So in the absence of magnetic field, what happens? All the magnetic moments are pointing in different direction. So if I add all the magnetic moments, the net magnetic moment will be 0. See, for the first arrow, if it is minus 2, second arrow plus 2, third arrow plus 3, and -3 or -3. So if I can just give some numbers. Okay, actually each magnetic moment is indicated by the Bohr magneton value. If I just substitute all the Bohr magneton values, and finally if I add, I'll get the answer to be 0. So it possesses significant atomic magnetic moments. Remember, atomic magnetic moments is the sum of both orbital magnetic moment and spin magnetic moment of the electron. So even in the absence of external magnetic field, the net magnetic moment of the material is 0. It is due to the randomly arranged equal number of opposite spins which are present inside the material. Then what happens when it is placed in an external magnetic field? What happens? The random arrangement of the magnetic moments will be arranged in the direction of the external magnetic field. They gradually change their direction, and then finally you can see the direction of the magnetic moment will be in par with the direction of the external magnetic field. Clear? So this is paramagnetic material. We have understood about the presence and absence of the magnetic field. Now list out the properties. So the first property, what happens? Lines of force attract because it readily allows the lines of force to pass into it. Then second property is susceptibility. Here the susceptibility value is positive and it is dependent on temperature. Unlike dia, which is independent of temperature, it is dependent on temperature. I have just given you a new equation here, that is susceptibility is equal to C divided by T minus theta. Here, this equation is referred as Curie-Weiss law. It is called as Curie-Weiss law. It's a law that connects susceptibility and temperature. Okay, here the susceptibility value is positive because it easily accepts the lines of force. And C is called as the Curie constant, theta is the Curie temperature. Then the permeability is greater than 1 here. Paramagnetic materials possess permanent dipole moment. That is, even in the absence of magnetic field, we have seen. Whereas in dia, magnetic dipole moment was absent. Then temperature dependent, no. So when the temperature is less than the Curie temperature, what happens? That is, the Curie temperature is it's like a critical temperature. When my temperature is less than Curie temperature, paramagnetic material becomes diamagnetic material. See, when the temperature is less than, on the bottom I have just given a small representation. See, when my temperature is less than the Curie temperature, let me fix the Curie temperature of each material. For the material which I have, for the paramagnetic material which I am going to consider, say example, it has a Curie temperature of 70 degrees Celsius. When I apply a temperature of 40 degrees Celsius, which is just less than that of the 70 degrees Celsius, what happens at that time? You can see that the paramagnetic material becomes a diamagnetic material. So the materials becomes the diamagnetic material. When the temperature is increased, automatically para becomes ferro. Okay. So this is the case in the case of paramagnetic material. So this is only will make you confused that when the temperature is less than the Curie temperature, para becomes dia. So para I have just given as a representation as P and dia representation as D. Okay, first point lines of force, second point susceptibility, which is positive. Then within the susceptibility itself, you have Curie-Weiss law connecting the temperature and susceptibility. Then permeability, which is greater than 1. Then the presence of dipole moment you are talking here. Then what happens when you decrease the temperature less than the Curie temperature, how the material changes. Okay, changes from para to dia is represented in the last point. And unpaired electron present. Okay, so each energy level, you can see the pairing of the electrons. In the last energy level alone, you have some unpaired electrons. Okay, now let us see the examples of paramagnetic material. The very first example is aluminium, manganese, platinum, crown glass. So usually in optics experiments, we use some prism. Okay, the prism is made of crown glass. So why the prism is used? It is used to find out the dispersive power of a particular prism. Okay, with the help of a white light. Then the solution of salts of iron and oxygen. So these are the 5 examples I've just given you in the screen. So among this, 3 is enough for writing the examination. Aluminium, manganese, platinum, crown glass, solution of salts of iron and oxygen. So these are the examples of paramagnetic materials. Okay, this is a small video showing the paramagnetic attraction. So in this video, you can see that this is actually liquid oxygen, okay, which is attracted by magnets. Within a few millimeter, you can see. So the liquid oxygen is being attracted. So this is gadolinium oxide, which is attracted. This is cupric sulfate. Once again, a paramagnetic material which is attracted. Aluminium, graphite. So in this video, what they have done is they have taken some 6 samples. Okay, 6 samples are taken inside a plastic container, and they have just made as a torsional balance. Okay, with the help of the magnet, they are trying to see whether each material attracts. Okay, see, they have a magnet, and each material gets attracted. So this cupric sulfate is a perfect example of a paramagnetic material. Okay, whereas water is diamagnetic material. Okay, this is about the paramagnetic materials, and we have seen some examples of it. See a small attraction nature you can see. So this video is being repeated in order to make you to visualize how they get attracted. These are all plastic containers. Okay, in chemistry lab you can see some salts like this. Even aluminium foil, you can just cut it into small pieces and can place near a magnet and can check whether it attracts. Okay, so this is actually a torsional balance which we have seen. That plastic containers are usually called by the name vials, VIALS, of paramagnetic and diamagnetic material, including graphite and gadolinium oxide, which we saw as a small video in the previous one. Okay, moving to the third type, ferromagnetic material. So in the periodic table, the most important materials are Fe, Ni, and Co. Hope you remember what is the real names for Fe, Ni, and Co. Iron, nickel, and cobalt. So like the previous two, we have to check what happens in the absence of magnetic field, in the presence of magnetic field, whether the lines of force are attracted or more attracted. What about the susceptibility value, permeability value, whether it is dependent on temperature or independent of temperature. All those properties we are going to see. So in the absence of magnetic field, see the arrows. All the arrows are pointing in the same direction uniformly. So this says that these materials have or show spontaneous magnetization even in the absence of external magnetic field. So there is a spontaneous magnetization. Okay, in dia we have seen there is no arrow inside. In para we have seen that the arrows were there, but each arrows were pointing in different direction. Whereas in ferro we could see that all the arrows are pointing in the same direction even in the absence of magnetic field. So this indicates that there is a strong internal field within the material which makes the atomic magnetic moments align with each other. So this phenomenon is known as the ferromagnetism. Okay, ferromagnetism. So in ferromagnetic material, we can see that I've just taken a ferromagnet in the form of a bar. Okay, inside the ferromagnet, you have several compartments like this. These compartments are called by the name domain. In each domain, you have the magnetic moments which all will be pointing in the same direction. See, for this particular domain, all the magnetic moments are pointing in the downward direction, which indicates that the magnetic moments are all parallel to each other. So even in the absence of magnetic field, magnetic moment is present. Okay. Likewise, in each domain wall, the magnetic moments are parallel to each other. The two domains will be separated by a boundary which is called as a domain wall. Okay, the magnetic moments in ferromagnetic materials have strong interactions with their neighbor magnetic moments. So this leads to a strong correlation between large groups of magnetic moments in ferromagnetic materials. So these large groups are known as domains. So several groups will be there and these groups are called as domains. This is in the absence of magnetic field. See, in this video you can see I have just taken an iron nail. So inside the iron nail, see the domain's orientation. Now I'm magnetizing the iron nail. Now all the magnetic moments are pointing the same direction. This iron nail now magnetized. It is capable of attracting a paper clip now. So after some duration of time, what happens? All the domains will reorient themselves and they go back to their normal position. Now the paper clip comes down. Okay, so this is just to show you the spontaneous magnetization, the presence of domains within the ferromagnetic material. Okay, the once again I'll show the video. Iron nail now magnetized. All the magnetic moments inside the domains point in the same direction. The iron nail attracts a paper clip. Even if I remove the magnetic field, iron nail still it attracts the paper clip and behaves as a magnet, but just for a shorter duration of time. Because of the alignment of the domain, so you get the nail get back to its original orientation. Okay, this is about ferromagnetic domains. So now let us see the properties of ferromagnetic material. I've just taken an ferromagnetic substance. Now it is placed in a magnetic field. The lines of force are just attracted more. So on the left side, I've shown you an electronic configuration of iron atom. Electronic configuration of iron atom. Okay, so this is the how the electronic configuration we used to draw: 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on. So when you while filling off with the electrons with upspin and downspin in 3d orbital, I can see some upspins. The more number of unpaired electrons are present in the 3d orbital. So these unpaired electrons are pointing the same direction, and it is due to the spinning of the electron we get a magnetic effect. Whereas in the 3p orbital, you can see that the electrons are paired. Hence, there is no magnetic effect which is observed because we need some unpaired electrons. So because of the unpaired electrons only, we get the magnetic effect. Okay. So how many electrons are here? 4 electrons are present in the 3d orbital. So looking back to the energy level, you have lower energy level, higher energy levels. Among the 4 energy levels, you have unpaired electrons in 2 energy levels. So for iron atom, you can observe that there are 4 electrons, 4 unpaired electrons, which are present in 3d orbital. So which is the peculiar behavior for ferromagnetic behavior of the iron. Okay. Properties. So lines of force are attracted more in a ferromagnetic material. See, lines of force are attracted more. They have permanent dipole moment and they act as strong magnets. They exhibit magnetization even in the absence of external field. So this property is called as spontaneous magnetization. And what about the susceptibility value? It is positive here and it is very much higher compared to paramagnetic material. And it is dependent on temperature. So when the temperature is greater than the Curie temperature, you can see that ferro becomes paramagnetic material. The same Curie-Weiss law is also applicable in ferromagnetic material. Susceptibility is equal to C divided by T minus theta. That is when I increase the temperature greater than the Curie temperature, ferro becomes para. And permeability value will be very much greater than 1. Okay, these are the properties of ferromagnetic material. Lines of force, dipole moment, strong magnets, spontaneous magnetization, susceptibility positive, high, then temperature dependent, greater than Curie temperature, ferro becomes para, and permeability is very much greater than 1. So from this slide itself, we would have able to identify 8 different points, 8 different properties of ferromagnetic material. Okay. Now, getting back to the examples. So 3 examples already you know: iron, nickel, cobalt. In addition, I am just giving you few more: gadolinium, dysprosium, and magnetite. So these are the examples of ferromagnetic material. Gadolinium oxide we have seen for paramagnetic material. When it is a single element, we can consider this to be a ferromagnetic materials. Okay, is the classification of magnetic materials clear? Students? So we have seen classification of magnetic materials just now. Okay, now the work for you is that you just look into my screen. So we are going to make a comparison chart now. We are going to draw a comparison chart. So you just open your physics note, and you have to draw a table what I'm going to draw. The similar type of table you are going to draw in your note. Okay. Okay. So just so this table should comprises of the 4 columns should be there. Headings are properties, diamagnetic, paramagnetic, and ferromagnetic. Okay, so 4 columns you have to draw. So in the properties section, first you have to talk about what happens in the absence of magnetic field. In the second property, you have to talk about the magnetic moment. Note down these things. Third property, in the presence of magnetic field, what happens? Then fourth one, whether unpaired electrons present or not. Presence of unpaired electrons. Then how they called? Weak magnets or strong magnets? Or I'll just you put this one, lines of force. Repelling nature, attraction, that one you can write. Then susceptibility, then permeability, then temperature. Then you have examples. Okay, like that, whatever properties we have seen so far,
Ma'am, repeat it again, ma'am.
it is in the screen, Ra. And last one will be applications. Where do these materials are used? Okay, once again I repeat, you can just open your note, you can just draw a table comprising of 4 columns. In the first column, you are going to write about the properties. Second, third, and fourth should be dia, para, and ferromagnetic material. Then I've just listed out some 10 properties, 10 parameters to be written. Absence of magnetic field, magnetic moment, presence of magnetic field, unpaired electrons, presence or absent. Then lines of force, can draw the diagram. So suppose north, south, then placing the diamagnetic material, what happens? The lines of force are just repelled away. You can draw neatly. Okay. So just for your understanding, I'm just showing you a small diamagnetic material placed in the center. So the repulsion you can show. Lines of force just repelled away. Like that, the same similar type of diagrams you can draw for para as well as ferro. The susceptibility value, it is negative, is positive, it is positive. You have to write in full form. So since the time is running, I'm just writing in a short form. But when you write in your note, you have to write in full form, like this: negative, positive, like that. You have to write fully. Permeability, mention the value whether it is less than 1 or greater than 1 or very much greater than 1. And the temperature, whether it is independent of temperature or dependent on temperature. And you have to show the susceptibility with the temperature. Uh, what happens to the when you increase the temperature? At last, some applications. Where do these three materials are being used? Okay, this is the task for today. So once you complete, keep it ready. Assignment will be activity will be created in Google Classroom, and you are supposed to upload it. Okay, so then and there you just find out the answers, prepare, make it as a PDF, and upload. Okay,
Time, ma'am. Due time, ma'am.
due time is 5 p.m. Okay,
Okay, ma'am.
okay, pa. So this is what I expect. I'll just show in the PPT also screen. Like that, you can frame a table. So if you are instead of writing in your note, if you are comfortable in typing in your laptop in Word file also, it's comfortable, or in a PPT also, you can just type the content and you can just upload the PDF. Either way you can do. I need some properties, 10 properties on the. So in the screen, some properties are missing. Don't look into. You just frame your own properties. Okay, so this is what we expected, and you have to upload by 5 p.m. today. Okay, so some missing entries are also there in the previous activity. So try to complete those. So regarding attendance, I've just included some Meet attendance extension here. So if you have joined by KLU mail ID, and in the same time, I will check the number of duration. If the duration is greater than 40 minutes, obviously you will get the attendance. Okay, clear students, if you just joined for 1 minute or 2 minutes, I cannot give you for attendance. So I'll just check the duration of your presence in the class. Then automatically your attendance will be given to you. Okay, so any other doubt in today's class? That's all. I'm not going to further continue with the next. We'll complete this in the next class itself. Okay, next topic will be about ferromagnetic domains and domain theory of ferromagnetism. I will share in the next class. Okay, so up to which I've just given you the materials also. You can just go through and complete this task by today. Okay, I think our class is over. 10:45.
Okay. Okay. Thanks, ma'am.
Thank you so much. Bye.
Thank you, madam. Bye, ma'am.
Thank you, ma'am.
Bye, ma'am.
Thanks, ma'am.
Have a nice day, ma'am.
Have a nice day. Bye.